All right, click this here. All right, so welcome to the first of a row of sessions that now deal with simulations of common envelope evolution. The organizers of the conference actually gave the session chairs the opportunity to give a bit of an introduction and talk a little bit also about work in their group. And I will actually take that opportunity to start out with a very brief kind of overview of a simulation, and that relates to what is going to be discussed in common envelope simulations, but also some of the questions that were raised yesterday. And then afterwards, we start with the first session talk. So let me share my screen quickly. So here, maybe I have to first start the, all right. Okay, so the thing I wanted to briefly discuss is a simulation or a set of simulations that were performed by my former master's student, Patrick Ondracek. So credit for this goes to him. And he actually looked into the effect of magnetic fields in common envelope simulations. And that's something that was raised by Ursula yesterday, and I wanted to add a little bit to that. The setup of the simulation that Patrick actually performed was rather standard, a 1 solar mass early AGB primary star with a companion such that the mass ratio of companion to primary star was, in our standard case, a quarter, but we also looked into 1/2 and 3/4. We performed these simulations with the moving mesh code ArrayPo with 2 million grid cells, but used adaptive mesh refinement so that we were able to resolve down to 0.2 solar radii. So don't be fooled by the images and movies that I'm going to show later. You will primarily see cores, cells in the outer parts of the domain, but close to the stellar cores, we actually achieve rather high resolution. We followed these simulations for very long. So these are our longest common envelope simulations, more than 500 orbits. And recombination energy was included via the Opal equation of state. And we assumed in these simulations local thermalization of the released recombination energy. And as I said, some of these simulations included magnetic fields. So here the magnetic field was initialized as a very weak dipolar magnetic field in the stellar envelope of the primary with a polar field strength of 10 to the minus 10 Gauss. Now the simulation looks like here. So what I'm showing in the next slide is the density. The stellar cores are marked with a plus and a cross. And you see the typical spiral pattern in the in-spiral. And then we follow the evolution for very long so that most of the material is actually ejected. You see how the density drops here. And we follow this out to 8,000 days. And by that time, the envelope has been removed more or less completely. And this is actually shown in this plot here. So blue is the orbital separation, the orbital evolution. And if you look closely, you see that there are two versions of blue here. So dark blue is the MHD simulation. And in the background, we have light blue. This is a comparison simulation with the same parameters, but without magnetic fields included. And you see that actually the orbital evolution is very similar in both. So magnetic fields have very little dynamical impact here, at least to that quantity, but also to the other important quantity, namely the unbound mass fraction. That's shown here in solid lines for the MHD simulations and in dashed lines for the simulations without a magnetic field. So gray here is the unbound mass fraction measured to one of the criteria, energy criteria that Ursula introduced yesterday. So this is the criterion that includes recombination energy that potentially could be released. But of course, to be sure that it really does and helps envelope ejection, one has to actually follow the evolution and then apply a more strict criterion for deciding about unbound mass. And this is actually then a purely mechanical criterion that includes only the gravitational potential energy and the kinetic energy shown here in orange. And you see once the recombination energy is released, also in the mechanical criterion, the almost complete envelope ejection is reached. So this goes up to 4,000 days, but we continue the simulation up to 8,000 days. Now, all this indicates that magnetic fields are rather irrelevant dynamically for the evolution of the orbital separation and envelope ejection. Now, if we look into the simulation from the side, we see the typical picture, this chimney-like structure that actually develops along the axis of rotation. And now you see again how the material is dispersed. Now, this is the MHD simulation. And if we actually compare this to the non-MHD simulation, we will see slight differences. So there is a hint of some material that gets that flows out along the polar directions, but that's very hard to see in density. So therefore, in the next movie, I'm going to show the radial velocity instead, and it becomes very clear in that quantity. So on the left-hand side, you will see a movie of the MHD simulation. On the right-hand side, for comparison, a movie that does not include magnetic fields. So this is how the evolution looks like. In the beginning, both simulations are very similar, but at about 1,500 days, we see a jet-like outflow to develop in the MHD simulation that actually develops rather strong, rather high velocities up to something like 100 kilometers per second. And this feature is completely missing in the simulation that does not include magnetic fields. So therefore, we attribute the jet-like outflow that we see here to a magnetic driving. This is illustrated in the next movies. Here is the magnetic field strength, and you see that the material that flows out is highly magnetized. In the very right-hand plot, you see the magnetic pressure over thermal pressure, and inside this jet-like outflow, the material is dominated by magnetic pressure. Now the question is, why do we see such a strong magnetically driven outflow? What actually gives rise to the formation of such a strong magnetic field? Well, magnetic field amplification in common envelope was studied by Sebastian Ullmann in 2016 already, but here in these simulations, we actually observe a new feature. This actually is late in the evolution, close to the point when the outflow launches, the two stellar cores come close enough to form a contact binary system, as you see here on the right-hand side in the zoom-in plot. Now, this actually gives rise to a second episode of magnetic field amplification, in addition to the known first episode that Sebastian described. So the first episode led to an amplification of the magnetic field energy by 15 orders of magnitude, but this happens mostly around the inspiraling companion star due to magnetorotational instability and shear instabilities. We also see some amplification of the magnetic field close to the core of the primary due to convection. But then the envelope expands and the magnetic field energy, here in linear scale in orange, starts to drop. But once the contact binary forms between the stellar cores and the outflow launches, the magnetic field rises again. And this is actually due to magnetic field amplification in these flows in the contact binary due to magnetorotational instability and shear flows. The situation that we find here is very similar to what Fabian Schneider observed in his simulations of merging massive main sequence stars, where also a strong amplification of the magnetic field was observed. So what we actually have here is not a toy model. So I want to emphasize this. This is nothing very set in magnetic fields, but this is actually a self-consistent end-to-end simulation of common envelope evolution and a launching of a jet-like outflow. Now, the flow morphology that we find in this 3D simulation is rather complex. It does not reproduce the idealized picture of a circumbinary disk. So we looked hard, but could not identify a clear circumbinary disk here. However, we still have the general symmetry of the setup, which actually leads to the formation of a preferentially polaroidal magnetic field along the chimneys of the common envelope structure. Now, inside these chimneys, the Alfvén Mach number is rather low. So this is a typical signature for a contribution of a blend for pain-like mechanism to the acceleration of the material. In addition, we have a magnetic pressure gradient of the colloidal field that also accelerates material, while in the chimney, the colloidal magnetic field contributes, as shown here in green. Outside of this chimney, the toroidal component is dominant, and here also additional acceleration of material can take place, similar to magnetic tower jets. So the situation is rather messy here, so different effects probably contribute to the launching of the jet. The outflow is replenished by accretion from material in the orbital plane, and this outflow then propagates through the collimating chimney inside a high-density cocoon, and this gives rise to these bow shocks that we see here with Mach numbers of 2 to 3. So in the end, we obtain a structure that resembles that of planetary nebula, of bipolar planetary nebula rather nicely. We can identify two different components of the material that's left behind, a toroidal component of material with slow velocities, 10 to 30 kilometers per second from the ejected envelope material, and then a narrow polar jet-like magnetically driven outflow with velocities of 90 to 130 kilometers per second. And the morphology of this is illustrated in the 3D rendering here on the left-hand side, is actually very similar to what we see in some of the planetary nebulae that were discussed yesterday. We have actually now found a mechanism that drives such and shapes such structures, and we find that it is rather generic. So we actually varied the mass ratios. We looked into this with different primary masses and evolutionary stages, even with massive stars, and we always find such outflows that are magnetically driven. And here, actually, for comparison to what was shown yesterday by Javier and Bruce, this is actually the temperature map that we find, and it actually, I think, nicely resembles what is seen in the observations of bipolar planetary nebulae. So with this, I would like to stop this short introductory presentation. And I think if there are questions, we can have maybe one or two, or otherwise continue with a later, more general discussion. Yes, Morgan, you have a question. You have raised your hand.
Yeah, so I wanted to talk a little bit about that flow that we're seeing at late stages. And it seems like you reach a state where the softening radii are sort of similar to the Roche-Lobe radii at that end state. And is that the case? Or
well, it gets close to this. So we are below this, but of course you actually run into that problem. So the thing is that in our simulations, we always adaptively reduce the softening length so that they don't overlap and they actually sort of stay small enough. But of course you get close to that. Yeah, that is a concept. Yes.
So, I mean, I think that it's really beautiful that you've traced the origin of the field amplification in the simulation, and then once the field is amplified, that it impacts the large scale flow in this really amazing way, and you get these multiple velocity components. But I just wonder if we should be, I don't know, do you really feel that it's fair to say that it's a self-consistent process in that we're not modeling, for example, the surfaces of those cores and the interaction of the flow with the surfaces of those cores at scales that are important?
Yeah, well, I mean, what do you mean by surfaces of the cores? I mean,
so for example, those may be finite size objects. There might not be, I saw sort of turbulent flow within the softening radius. Like, how does that affect these things?
I mean, the scale that you look at here in this late stage when the quantum-binary forms is actually, you have sort of a distance between them that's something like 25 solar radii still. So that's still large compared to the cores that you would actually expect to have there.
And what is the softening radius relative to the Roche-Lobe radius at that point then?
It is smaller, so we have checked that. I don't know the exact numbers. I would have to look that up, but
yeah.
It's smaller.
I mean, it's really beautiful, and it's really interesting to think about these things. And on some level, it feels to me like at late times when cooling starts to be effective, radiative cooling. Some of these processes may be even stronger than you're seeing, because by sort of reducing the pressure of the gas, you might amplify some of those relative velocities of fluid parcels that are next to each other.
Yeah, that depends on the cooling timescale, of course. And, yeah.
Right, but the cooling timescale is a variable quantity with time as this gas is clearing.
Okay, yeah. So there are other raised hands. So Logan, you have a question?
Yes, thank you. So sorry if you mentioned this already, but was the MHD scheme used for these simulations the constrained transport theme by Mox?
No, it's not constrained transport. It's actually the standard scheme that Repo has. So it's the power scheme that Rüdiger Hagmo implemented.
Okay, thank you.
Hagai, you also have raised your hand.
Yes, I was wondering about the when and where do the recombination energy it kind of takes place, or when does it become really important?
Well, I mean, you can see that kind of from, well, I have to share the screen again, from the plot that I showed in the beginning. So I hope that I can go back here. No. Let me share this again. So here, sorry. Okay, so the formation of the outflow is something like at 1,500 days. So that's about here, right? So that is actually when you have ejected already quite a bit of material, so 75% of the envelope. So by then, quite a bit of recombination energy has been released already, because without that, you would actually release only something like 20% of the envelope material.
So it seems that, okay, so but it seems like 70, no, as you said, usually you just see the ejection, at least in terms of the kinetic aspect, we see ejection of about 20% at the end, right? Here we see
we follow this actually very long. So the kinetic energy criterion is the orange here that I've shown before, and so that also reaches 100%.
Yeah, no, in this simulation certainly. I was wondering about when it happens, and what you said it's 5,000 days, but it's 5,000 days. We already see about 75%, right?
It happens at 1,500 days. The outflow.
1,500. Okay, 1,500 days. Oh, sorry, no, I didn't hear correctly. Okay, and how did you check the assumption on how local is the recombination energy put, and how does that affect?
Well, in this simulation, we did not check this. So actually the setup here is the same as used by Christian Sand, and he looked into this, right? So here's actually in his paper. So it's the same setup actually now with magnetic fields added. And so as far as we can tell, so most of the recombination energy release happens at high optical depth. So that should be a safe assumption. But of course, I mean, the assumption that it still goes in here is the local thermalization that has to be still checked. Right. So I don't see further raised hand. I would actually like to now proceed to the real first talk of this session. We can discuss these things later on if you're interested. But now I would really like to ask Logan to share his screen and start his presentation on moving boundary conditions and common envelope simulations.
Sure thing. Thank you, Fritz, for that great introduction. Can you all see my slides?
Yes, I see them.
All right, sounds good. So thanks for having me. My name's Logan. I'm a grad student at UW Milwaukee, and today I'll be talking about my simulations of CEE. I'm going to talk mainly about moving boundary conditions, but at the end I'm going to also throw in some stuff about some of our preliminary MHD results. I work with Phil Chang, my advisor, as well as Vanaya Valsan, another grad student. She will be giving a talk tomorrow dealing with how to get observables from our simulation results. And I know that's something that came up during the discussion at the end of yesterday, so that might be something to keep an eye out for. So I'll just give my little spiel about moving mesh codes. There are two main codes that are used in types of codes that are used in computational astrophysics. There's smooth particle hydrodynamics and Eulerian good codes, and moving mesh codes are kind of a hybrid between the two. We generate the mesh using what's known as a Voronoi tessellation, which you can see there on the left, which can move and deform along with the fluid. So the code that I use is known as Manga, which has been applied to CEE as well as stellar mergers and tidal disruption events. So today I'm going to be focusing on moving boundary conditions. So this is a way that we can create a sort of solid object within our simulations. And how we construct one is we take a bunch of those Voronoi cells that I just showed, and instead of letting them flow around each other as they normally do, we glue them all together and constrain them all to move together as one rigid body. We also impose reflective boundary conditions on the outer surface so that nothing can pass through it. We then allow the boundary to move just as the cells do in response to the external forces that it feels, as being gravity and gas pressure. So in the top diagram there, you see a very rough PowerPoint sketch of what a moving boundary looks like. And then on the bottom, you see a more realistic test case of a spherical boundary that's subject to a supersonic wind. You see the shock forming there. So it's a test case that will be relevant for when we apply this to common envelopes. Instead of reflective boundary conditions, these can also be easily extended to inflow or outflow conditions. But for the work that I'm going to present here, that won't be relevant. So the motivation for using this technique for common envelopes is that typically simulations of CEE model the companion object as a point particle. And this is certainly appropriate if the companion is something like a black hole or a neutron star, which is incredibly small. But it's unclear how well the approximation holds up when the companion is a larger object, like stellar sized. In this case, you can have hydrodynamic interactions with the surface of the companion. You can have material that accretes onto the surface of the companion and then creates a shock, which back reacts onto the envelope. And so those interactions could change the dynamics of the spiraling. So ideally, what we would do is we would fully model the internal structure of the companion, but in most cases, this is just not numerically practical. So the next best thing we can do is, since the companion is much more dense than most of the surrounding envelope, we can instead just model the companion as a hard boundary. And so this is where our moving boundary conditions are going to come into play. So I'll go ahead and show you some of our results for just such a simulation. We start out with a red giant plus a stellar-sized companion modeled as a moving boundary. In this case, I believe it is size 2 solar radii, although that's hard to see at this scale. We set the giant in co-rotation with the initial binary orbit. We also do some mesh refinement near the position of the companion object because we need the surface of our moving boundary to be well resolved. And let me just go ahead and start off this video. So you see what's pretty typical of a common envelope phase, right? Nothing crazy here. You see the spiral in, all the gas is thrown out. So we've done these simulations for 5 different companion sizes, ranging from 1 to 3 solar radii. See what the effect is. And so the principal difference that we see between these simulations and ones that we did previously that used a point particle companion is that now the companion experiences some hydrodynamic drag. So let's take a look at that. On the left, we see the drag experienced by the companions over time. And so the spikes are when the companion reaches periaps. And pretty unsurprisingly, we see that the larger companions experience more drag. In the plot on the right, we plot the average drag experienced by each companion relative to its radius. And follows a pretty linear relationship that agrees with a simple theoretical estimate that just comes from computing what the ram pressure would be on the companion. Okay, so you've discovered this extra drag that the companion experiences, but the question is, does this actually have any meaningful effect on the Conran envelope? And so for that, we have to look at the orbital parameters. We've found that the size of the companion actually has little to no effect on the semi-major axis of the orbit. However, the eccentricity is significantly different. We find that larger companions result in lower eccentricity overall, probably because the larger drag force helps to circularize the orbit. Note that since the orbital energy is a function only of the semi-major axis, and the semi-major axis doesn't care about the companion size, this indicates that the energetics of the Conran envelope phase are not affected by the size of the companion. This is also substantiated by the fact that, I don't have a plot of it here, but if you look at the amount of the envelope that's ejected, it's basically the same for all 5 of these simulations. But the fact that the eccentricity is different indicates that the size of the companion affects the transport of angular momentum from the binary to the envelope. We can also check that by looking at the torque that's experienced by the binary, which you can see there on the right, where we've plotted the torque from gravity and from hydrodynamic forces, and then the total. And we can see that although the hydrodynamic torque is in general much smaller, it is significant over a few periods of time. And another sort of interesting result is we see that both types of torques can change in sign over time. For the hydrodynamic torque, that's because initially you have a lot of material building up behind the companion, so it actually kind of gives it a boost, and then at later times you have the companion crashing into the more dense material towards the center of the giant, and so it creates a drag. And then the gravitational torque changes sign just as a result of the orbital phase. Right. So for the remainder of the talk, I'm going to talk about some of our preliminary results for using magnetic fields in CEE. So we have a new MHD module in Manga. It uses the divergence cleaning scheme proposed by Dedner and the HLLD solver implemented in Athena. So this is surprisingly relevant to the results that Fritz talked about in his intro. Instead of using an initial dipole field, we use a field that was proposed by Ludikov, which is similar to a dipole field. In fact, outside of the star, it is a dipole field, but inside, a dipole field diverges at the origin, so the Ludikov field is just a bit more spread out inside the star. So if you use a dipole field, you initially get a big advection of magnetic energy out from the center of the star. So what we find is that in the first several days of the common envelope phase, we see a very rapid amplification in the magnetic energy, particularly near the companion, and particularly the toroidal component of the field as well. We don't find this to be dynamically important, at least over the time scale that we're running right now. But as we saw yesterday, and I believe Guillermo's talk, is significant at later times for shaping the nebulae. This seemingly strange, huge amplification of what was that, at least 15 orders of magnitude in a few days might seem surprising. It's actually eerily similar to what was found by Ullmann back in 2016, which is especially surprising since Ullmann used both a different initial field and a different MHD scheme using the Powell 8-wave scheme. So this is kind of an encouraging result since this confirms that the amplification is robust to which MHD scheme we use. So obviously this hasn't been run for even 100 days, I think, so it's not really long enough to see the outflow properties that Fritz talked about, but so far it is looking promising. And with that, I'll just reiterate my main points. So we find large amplification of the magnetic field in the early stages of CEE when we include MHD, which matches Ullmann's results. We can model the companion object realistically using moving boundary conditions. And when we do so, we find that hydrodynamic interactions affect the eccentricity of the orbit. So thanks, and I will be happy to take questions.
Thank you very much for this great talk. So questions? Yeah, Gloria, you have a question. Please go ahead.
Yes, good morning, good afternoon, good evening. Thank you for that very interesting talk. And I think it's a really important step forward to start analyzing in detail what's happening around the companion, as the companion is immersed in the primary star's envelope. I had two questions. I don't know if I missed it. Is your simulation performed with a constant orbital period, or do you can you feed back the energy loss and do you have the spiral in? That's the first question. And then the second issue has to do with the reaction of the primary star to the presence of the companion. And I realize that you don't have that included in your simulations, but is there any possibility of eventually including the tidal effects that the secondary causes on the primary in terms of how this modifies the envelope into which the secondary is spiraling in? Thank you.
Thanks, Gloria. So I'll answer the second question first. So we sort of model the tidal interactions leading up to the common phase in that we spin up we give the giant an initial spin. We put it in co-rotation with the binary orbit. So of course that the structure of we're still using the structure of the giant as if it were static, right? So that's not entirely correct for us to do that, but that's definitely an interesting problem. I know that Morgan and his group have done work on before the onset of the common envelope phase, like how do the tidal interactions affect the primary, right? And so that's something that I've been wanting to try to implement more into our simulations for a long time, but I haven't really gotten around to it. And let's see, the first question was, we start the simulations with the companion in a circular orbit around the binary. Of course, it doesn't stay circular for long. So I believe the orbital period starts out at 20 some days, and then toward the end of the simulation, it's down to maybe 12 hours or so. But we have to modify that slightly with the moving boundaries because due to the mesh refinement that we do around the companion, to keep that, to be able to insert a finer mesh around the companion, we, instead of putting the companion at the surface of the giant, as is typically done, we move it out a little bit just to give it some breathing room for us to do the mesh refinement. And so the orbital period is a bit longer for those ones. It's possible that could create a larger eccentricity in general for those simulations, but of course it wouldn't account for the differences in eccentricity between those simulations that I showed in this talk. Right. I hope that answers your questions.
Thank you very much.
Okay, Jason, you're next, I think.
Hi, Logan. These are very nice simulations. So I just had a question, because one of the things I was sort of picking up on from what Fritz was showing earlier in his simulations, and then what you're showing in yours, is that you're seeing most of the amplification sort of, near the companion, or that's where you're sort of getting, the strongest fields. And I was just thinking a little bit more about this, right? So like in these simulations, you've got a source of free energy and differential rotation from the shear in the gas. That's there no matter, in both of your simulations. It's quite substantial. but if you think about like dynamos and nonlinear amplification of the field, the other source of what you need here is a source of helicity. And I think this might be true, but I don't know. It would be interesting if you comment on it. These stars, giants, will have, they're just huge sources of helicity because they're convective. And so I'm just wondering, if you started with a convective simulation where the gas was all, bobbling around with helicity in it, if you would see something very different from what you're seeing here, where it's the local helicity sources where like sort of you're seeing the field amplification. I don't know if there's anything you can comment on about that.
Not really. So we just start out with, we take a MESA 1D profile and map it to a 3D star, right? So it doesn't really start out with any convection or anything in it. So I can only speculate that would, including that would further amplify the field, but I can only guess at this point. That's an interesting question.
Cool, thanks.
And Ryu, you're the next question.
Yeah, thank you for the nice talk. I had a rather technical question, but so as you like glue together your moving boundary particles, I think there's a subtlety in how you do it, but do you let the boundary particles to have a spin eventually? Because if you have like a large moving blob, it can have a moment of inertia that's like some fraction of the orbit. So eventually, if you let the orbit spin, it can change the final separation.
Huh. That's an interesting question. It is allowed to spin. I don't know if it really acquires any spin. It's because
so I guess that also relies on how you define the boundary itself. Like if you're using a perfectly reflecting boundary, maybe it doesn't get taught
right
properly,
because at the surface it's not a no slip condition. It's just a no mass can pass through the surface. So it could acquire a spin, but I don't think it would acquire much of one.
Okay.
So in answer to your question, I guess I haven't considered what the spin of the companion. I just assumed it was negligible, but
well,
I'll check on that now that you've mentioned that.
I guess it depends on the moment of inertia ratio between the star and the orbit. So yeah, it might be interesting to look into it. Thank you.
Yeah, it would. Thanks. That's a good idea.
Okay, so then the last question by Sagif. Oh, Hagai, you also have a question. So first Sagif, then Hagai.
Hi, thank you for the talk. So maybe I missed that, but when you change the companion radius, did you change the mass of the companion? And also, can you comment about accretion? If how the companion may accrete, it may have changed its radius, so it can affect the result.
Right. So we use equal mass companions in each of these cases, regardless of the size, just to have one less variable to worry about, really. As far as accretion goes, yeah. So you would have you definitely have material that builds up around the surface of the companion. It's not allowed to enter the companion because of the reflective boundary condition, right? But you do have additional mass that's building up there, which in the end also increases the drag felt by the companion. Something that I have been wanting to investigate, but I'm not quite sure how to go about it, is allowing it to accrete by setting the companion to be an inflow boundary, right? So mass can just enter it, and then it's taken out of the simulation, right? But it's not clear to me what the appropriate thing to do is since we think the companion is a star, right? Because it's going to, some of the mass is going to be accreted onto its surface, but we can't just treat it like a black hole where everything that falls onto the star is just part of the star now, right? If you have stuff fall onto the star, it's going to puff up. It should puff up, So, so in answer to your question, it doesn't, it accretes in that we let mass build up around the gas cells surrounding the star, but not actually being part of it.
Okay, and then Hagai, next question.
So actually 2 short questions. One, can you show the eccentricity evolution again?
Certainly.
So this is actual eccentricity. It starts from 0.5.
So this is, it looks a little noisy because it is interpolated. Because we're not in a, it's not a Keplerian potential, right? You don't just have 2 masses, you have all these gas around too. So you can't just compute the eccentricity from the orbital elements as you would normally do. So what we do is look at the separation, the separation between the core and the companion, right? Look at where it hits perigee and apogee, and then use those to kind of interpolate what the eccentricity should be.
No, that is well understood. But I was wondering about the very high eccentricity. I don't think I ever saw such high eccentricity if you started from circular orbit. It's like starting from 0.5.
Yeah, well, the estimates at those early times are kind of shaky because at that point, the binary has only been through a couple of orbits, right? So you don't have a whole lot to interpolate to get your eccentricity, right? So that could be why the eccentricity is kind of high at the very beginning. But I believe.
Sorry, can you show the evolution from 0 to that high point? Because it started with 0, right?
With 0, with 0 eccentricity, yeah, sure. Well, so I don't have values earlier than about 20 days just because of how the eccentricity is computed, right? We need it to reach at least 1 apogee and at least 1 perigee before we can interpolate the eccentricity. Like, certainly it really starts at 0, right? We know that, but just the algorithm that I'm using to generate this plot can't handle that.
Okay, and the other question is, so I just was wondering whether you verified angular momentum conservation. I guess you did, but I just wanted to check whether everything is fine and what level of conservation do you see?
Oh, conservation properties. I don't have those plots on me, actually. I don't know if I can even speculate since it's been a while since I've seen them, but
okay,
mass is conserved well.
Yeah, we can check it offline. That's what I was wondering about it.
Okay.
It's really interesting about eccentricity. We're also working on stuff like that. I was really wondering about those issues. Thank you very much.
Yeah. Okay, I'll get
A
back to
very
you on
brief
that.
question. If you have one, Steve, then please go ahead.
Just a suggestion that a way of treating the boundary on the accreting star, sorry, on the companion, maybe instead of having an accretion condition, just have as a change in the nose slip a shear layer. So the equivalent of a boundary layer. That I think you might find that there are some interesting changes resulting from that, especially in the orbital evolution, especially in the eccentricity.
Sorry, what do you mean by a slip layer?
A boundary layer.
It should be a
So you
turbulent
mean-
boundary.
It's a sort of subgrid treatment of
Yeah,
a
yeah.
kind of turbulent convection, turbulent viscosity. So just figure what the shear is between your wall, your solid body, and the next grid point outside it, and just treat that as the equivalent of a boundary layer.
Okay. I see
But the
what
thing
you're
that
saying.
worries me is to come back to the stupid question from me that I had from yesterday is this treatment of internal rotation. If one were going to do it in something kind of squishy, compressible, and can potentially something that can go into differential rotation. So you think of what would happen if you had a Jupiter-like object, that you're going to have nested cylinders and not nested shells. And this is going to really change the way the angular momentum is distributed in the object. So I have the feeling it will make a big difference in the way the eccentricity of the system changes at the beginning, and especially also your torques, which is really nice to see. I mean, that's a wonderful effect. Almost looks like a von Karman sheet, but just some suggestions, okay?
Yeah,
very
yeah,
nice
good
work.
suggestion. Thank you. Thanks.
So I think we have to move on now. If there's there will be more time for discussion later on. There's a discussion session at the very end of today's program. So I would ask Morgan to actually share screen now. Logan, if you have stopped sharing already, or maybe you have to stop your screen share before. Oh yeah, all right, now it's working. All right. Okay, so Morgan, please go ahead. I'll give you 2 minutes warning.
Okay, fantastic. Hi, everyone. Well, thanks so much for bringing us all together. I think it's, a wonderful relief in some ways from the reality of daily life to get to think about something like common envelope. And so it's a delight to have all of this intellectual energy together. And I'm excited to be talking about these things with you all. So I want to talk about thinking, I think, really kind of thematically in terms of some of the breaking down these phases into their component parts. I want to talk about some of one aspect of the lead into these phases and of common envelope, and that's the role of tides. And in particular, I'm gonna, for specificity, I'm going to talk about neutron stars in common envelope phases. And so if we think about the formation of a double neutron star system that eventually merges under the influence of gravitational radiation, one pathway there is that you start with two massive stars, one explodes and leaves behind a neutron star remnant, and then you have a common envelope phase that consists of a neutron star and a companion. There are, as I'm going to talk about in a moment, there are other pathways to making a double neutron star, we think. But just for the sake of specificity and putting some concrete sort of numbers, that's what I'm going to use today. Okay, so if we think about what happens in the evolutionary steps leading up to that phase, there is a supernova explosion, and there's mass loss accompanying that supernova explosion, and there's potentially a kick to the newly formed neutron star. Both of those things have the effect of basically scrambling the orbital angular momentum, vectorial direction, and magnitude relative to the initial condition. And so typically orbits will become less bound, but also potentially spanning a wide range in eccentricities in that moment. And so the situation is then that we have an evolving star with a neutron star companion. And in general, we may have a broad distribution of eccentricities at this moment. And one question we can ask is, do tides act to circularize these orbits on the time scale that the star is changing due to stellar evolution, so that when we start a common envelope phase, we're talking about a synchronously rotating donor star that's tidally locked to its companion, and we have this kind of classical Roche-Loeb overflow scenario? Or do tides not act sort of sufficiently on those timescales, and we have a kind of qualitatively different scenario? And so in this binary scenario, which is what I'm going to focus on for specificity here, this is a competition between the donor's expansion, the stellar evolution rate, and tidal dissipation. And in the back of your mind, maybe you can keep in mind that there are triple systems, for example, in which eccentricity is being driven, for example, by a secular orbital evolution process or a torque. that might mean that it's a competition between tidal dissipation and some other process other than stellar evolution. So kind of qualitatively, the lessons here are the same in both of those cases, but we have to pick something specific. So that's what I'm talking about. So first, let's talk about the radius growth timescale. So we know that these binaries, in a sense, start out non-interacting in that they're just orbiting along. And then over time, the radius of one of those components is growing, and it starts growing to the point where at periapse, there starts to be some level of interaction between the gravitational potential of this orbiting companion and that star. So the radius growth timescale, of course, is this sort of stellar evolutionary property. It depends on the nuclear evolution at the core. As the luminosity of that burning layer changes, the outside layers puff up. That depends on the type of star, it depends on the mass of the star, it depends on the stellar evolutionary state. The tidal dissipation timescale also has dependencies. It depends on the spectrum of oscillatory modes that are excited by the gravity of this companion. It depends on the dissipation process, which in turn depends on the structure of the star, and in particular, whether it's radiative or convective. So we'll come back to that in just a moment, but I mentioned kind of the spectrum of oscillations that are excited. And when a gravitational potential is time varying in the frame of the stellar material, the fluid will oscillate around hydrostatic equilibrium. And so it can't be instantaneously in equilibrium with the gravitational potential without some very strong dissipation mechanism. So lacking a dissipation mechanism, we get an oscillation. And so examples of a time varying potential for the stellar fluid are an eccentric orbit. Then it's kind of easy to see that the gravity of the companion is going further away, closer together. That's going to sort of impose time variation. Or non-synchronous rotation will impose variation as the stellar fluid sees it. So an example, a counterexample in a sense of a non-time varying potential would be this case of a tidally locked orbit in which the stellar fluid always experiences the same gravity. So oscillation then imposes this dynamically oscillating tide, as opposed to sort of fluid that's in equilibrium with a gravitational potential, which might contain the gravity of the two objects. Think like a Roche-Loeb potential. So we talk about tidal oscillations in terms of spherical harmonic basis functions. So we describe them with a degree L, azimuthal order M, and then a radial wave number N. So L, M, and N together kind of characterize an oscillatory mode. And if we think about dissipation, I mentioned that it really matters whether there's a convective stellar envelope or a radiative stellar envelope. In a convective stellar envelope, the modes that are going to be most excited are called the fundamental modes. These are modes with no radial nodes. And they have typically the most excited mode, though not always, will be the quadrupole. So like as in this cartoon, sort of two-lobed, L of 2, M of plus or minus 2 mode. Now, when there's a radiative envelope, that structure supports sort of buoyancy modes. And those have lower frequency than the fundamental mode, and they can have relatively high radial wave number. And those often are excited because their lower frequency can more closely match the orbital frequency. So when the forcing, if you think about a driven harmonic oscillator, when the forcing more closely matches the natural frequency of the, say, pendulum, then the amplitude is larger. And the situation is the same here. these modes in the convective envelope dissipate because you have a coherent sort of velocity pattern of the oscillation, this non-radial oscillation, but it's interacting with the chaotic velocity pattern of the turbulent field. And so the dissipation rate depends on the properties of the turbulence, like the turbulent Mach number, that sort of thing. And we'll see that because turbulence depends on the properties of stars, you can actually estimate the dissipation associated with things like the luminosity of the star's mass and radius. The G modes, these buoyancy modes, dissipate through sort of radiative losses near the surface. And on average, and this is a very sort of overgeneralized statement, that radiative damping tends to be much less efficient than the convective damping. Now, I'm going to show a few slides from some really kind of fantastic work by Alejandro Viña-Gomez. Alejandro's on this call, so I hope during question and answer that you'll chime in also. So what Alejandro did is used binary population synthesis models to assess the properties of the common envelope phases that go into eventually forming a double neutron star system in that model. And I think this is a really useful kind of iterative approach to take, because then we can ask, well, what are the common envelope phases that we should be investigating in more detail? And what are the steps that are happening in that population synthesis? And over time, maybe we can improve those recipes and sort of move forward. In any case, we're highlighting here the stellar type of these stars. So these tend to be stars that are on the order of 10 to 20 solar masses. These are the donor stars. And they, as you can see here, are typically between 100 and 1,000 solar radii at the time of dynamically unstable mass transfer. Now, we can ask, what are their eccentricities at this moment where dynamically unstable mass transfer starts? And what Alejandro did is started with 0 eccentricity for the initial conditions of every single binary. And the reason for doing this is not because it's completely realistic, but because it lets us sort of pick out what's going on in exquisite detail here. So there's a population you can see of sources with 0 eccentricity. And then there's a population with a broad range of eccentricities. And what's going on that separates those two? It turns out that the population, we're looking at mass ratio here. And so the population with 0 eccentricity are stars that are close enough in mass that they both evolved to the giant branch at similar times. So that's this population with mass ratio of 1. And those then retain the original eccentricity that we imposed, which was 0. So these are sometimes called a double core common envelope because you have essentially 2 giant stars that are interacting. That's a super interesting thing for us to sort of learn more about in the future. But there's this other population, which is the majority of sources in this model that contain a neutron star and this massive star. So that's a mass ratio of about 1 to 10, maybe 1 to 15 in some cases.
2 minutes.
And what Alejandro finds is if he evaluates sort of the simplest estimate of the tidal circularization timescale compared to the timescale that the radius of the donor star is changing over, there's a huge range in the ratio of these timescales. And there's some systems that seem to have a circularization timescale much shorter than their radial growth timescale. And those we expect tides to act to circularize before the common envelope phase. But there's some that are in the opposite regime, and maybe tides don't act to circularize those orbits. So I followed up on this in some work with my colleague Michelle Vick, who isn't here today, but I'm sure would be delighted to talk with anyone about more of these details. And what she did was implement a more sophisticated modeling of first the spectrum of dynamical oscillations that are excited in a given periastron passage. And then from a sort of linear theory approach, and then they're modeling the dissipation of that spectrum of modes against a given convective velocity field. So I'm showing you here the estimated sort of dissipation rate and circularization properties. So an estimate of a tidal dissipation rate, so units 1 over time, on a convective field has to do with the mass of the convective envelope and some properties of sort of the ratio of the effective viscosity compared to this characteristic scale height. And if you put in some really sort of order of magnitude estimates, you get this ratio of the luminosity and the mass radius squared. And what this plot is showing is as a 15 solar mass star grows in radius, how it develops a convective envelope, and how the effective dissipation, both in this simple estimate in the dashed line and in the sum over modes, evolves. And then what Michelle does is evaluates the orbital evolution of systems that start with a given eccentricity and periapse distance. So those are the two axes of these plots. And then evolves those up to the point where the donor star fills its Roche lobe at periapse with a 1.4 solar mass companion. So a mass ratio of about 1 to 10 here. And what we see is that in a lot of this parameter space, the systems retain similar to their initial eccentricity. But in some portions, especially with wider initial periapse distances, there is essentially time for tides to act to circularize the orbit. And that even when we start with an initial eccentricity of 0.5 or 0.6, we end up with an eccentricity at Roche lobe overflow of close to 0. Since we're evolving the spin of this donor star, and we're imagining it in solid body rotation, which is of course not true, but that's what we can kind of do in this semi-analytic approach. What we see is that even when the orbit circularizes, it doesn't tend to be synchronous. So we see very few cases here of truly synchronous rotation. So as one visualization of that, if we start with an initially thermal eccentricity distribution of systems that contain a neutron star and a 15 solar mass companion, then here's the final eccentricity distribution. And basically many of those systems stay eccentric at the time of Roche lobe overflow, and a small fraction on the order of 10%, all coming from those with convective envelopes, circularize. And I think what this means is that when we think about the onset of common envelope phases, in particular in these large mass ratio systems where we have a massive donor star that's evolving in radius very quickly, and a much lower mass, perhaps compact object companion, we can end up in situations where we get dynamical tides with very large amplitudes, or eccentric mass transfer. And there's really interesting sort of properties of the tides as they become nonlinear, start to dissipate. The objects develop sort of differentiated structures and differential rotation. And maybe that sort of pantheon of possibilities is actually kind of not like the oddball, but the sort of typical lead into a common envelope phase in these sorts of systems. And so I think it'll be really fun to explore that more in the future. So thank you all.
Thank you. So questions. I think, Sagif, your hand is still open from the last up from the last question, right? So then we would have the first question by Gloria.
Oh, yeah. I'm fast to raise my hand. So this is a really complicated problem. Eccentric binaries are really, really complicated beasts. And the first thing I would like to comment, I don't know if I misunderstood, but even if you have synchronous orbits, synchronous meaning that the orbital period equals the rotation period, if your orbit is eccentric, you will excite a broad spectrum of oscillation modes.
Yes.
Right? And the other comment is that it's not only the radial perturbations, the perturbations of the donor in the radial direction, but it's also the azimuthal motions of its surface and inner layers, which are acting here to produce the tidal dissipation. And so when you go to that point of view, what becomes really important is what viscosity you're using. So if you're using molecular viscosity, the tidal energy dissipation is really quite irrelevant. It's very small, right? So but if now you incorporate the possibility of turbulent viscosity, which seems to be what most people are doing, and models of the sun, for example, have this very large viscosity, then the tidal energy dissipation rates can be very large, and they can help the star to become bloated. So we explored this a few years ago in the case of this red nova, B1309 SCO. And it turns out that you could actually get a star to bloat fast enough to cause the in spiral. So I guess what I'm aiming at here at this point is when you do your simulations, what type of viscosities are you using, and do you have an expression for calculating these viscosities? Are they just input parameters? Thank you.
Yeah, so those were some really beautifully stated points, and those questions are of central importance to the outcome of what happens. So I think it's really important to raise those. So in the calculations that Michelle was doing, she was looking at the spectrum of modes that's excited in the linear theory, and then we were looking at the dissipation of those modes against the convective velocity field, so the essentially the turbulent effective viscosity, and so that's what we were looking at in that calculation. These two cases that I'm showing you on the screen, one is a case of a circular orbit on the left with asynchronous rotation, and as you can see, there's a mode with L of 6 or something, reaching high amplitude and sort of breaking and dissipating into turbulence. So those are cases where we're not explicitly adopting a parameter for sort of dissipation, but we're just sort of looking at the hydrodynamics of a very extreme mode, which will not determine the sort of lead-in, but is just a sort of example of what's possible in a hydrodynamic simulation where you can only look at things when they have very large amplitudes, sort of comparable to the size of the star, just because of your resolution limitations.
Okay, so then I think we can still have two more very brief questions and brief answers, so to give everybody the chance to grab a cup of coffee as promised for the 10 minutes break that we'll have afterwards. So Noam, please go ahead.
Yes, a very interesting and important study. I just want to point out to the system of post-asymptotic giant branch stars with high eccentricity and a little or quite a massive companion that there was a talk yesterday about this orbital period of 100 to 300 days, and there the eccentricity is about 0.3. And we think, some people that mass loss during periastron passages can also increase the eccentricities. And I expect the neutron star to accrete mass, launch very strong jets that can remove envelope mass. So I think this is also an important effect in all this mechanism.
Yeah, so once mass transfer starts, the eccentricity evolution is very interesting as well, right? And it probably depends on the microphysical processes of like whether you're launching a jet and how that impacts the surroundings. And yeah, so when we look at systems that are kind of after the fact, is I guess how I would try to think about those post-AGB systems. You know, I guess it's maybe we have to think about the multiple steps that might have got in us there. So
yes, and we know they launch jets. I mean, they have strong jets, and so relatively strong, not as neutron stars. Okay,
right, right. So this is a really beautiful point. And another sort of puzzling sort of set of systems are there's the enormous population of Sloan post-common envelope white dwarf main sequence binaries that's in the series of beautiful papers by Zorotovich. And then there's some systems that are seen by their gravitational self-lensing. And at least one of them has eccentricity of sort of moderate, like 0.3, and orbital period kind of between the stable Roche-Loeb overflow and post-common envelope nominal separation. So I think we have a lot of thinking to do about where sort of post-common envelope eccentricity might come from. Like, you know, it's easy to imagine, oh, there's gas, it's just going to dissipate, but that may not always be the case when we think more carefully.
Okay, so the last question was sort of lost now. So I think then we would actually start coffee break until 20 past, I think it's then 2 UTC. Okay, so then the next talk is by Emily Wilson. Is she there? Oh yeah, all right. Please go ahead, start your screen. Okay, I'll give you a 2 minutes warning again.
Great, thank you. Okay, good morning, afternoon, evening, tomorrow, who knows. So I'm going to talk about convection, and this is my official title, Convection as a Key Ingredient in Common Envelope Evolution. My name is Emily. I'm a PhD student at RIT. I'm in my final year, and I'm being advised by Jason Nordhaus. So this is my official title, but my better title is It's Time to Make the Convection Connection. And so I hope that this is a little catchy and you'll remember it. So it's time to make the convection connection. So I work on convection in CE evolution. So convection in low mass stars takes up the large majority, the vast majority of the envelope. And this, what I'm showing here, is a 4 solar mass star, and the blue line is the convective transport time scale. And the dashed lines are in spiral timescales of M dwarfs or a couple Jupiter-sized things. So the convective transport timescale kind of defines these convective regions within the star. This is just from a MESA model. And there's 2 convective zones. There's this one that I've shaded in yellow that's defined by this timescale. And then off of this plot, there's a secondary convective zone that I've shaded here in pink. And the convection that I'm worried about is the convection that is just touching the surface of the star. And we call this in our papers the surface contact convective region, because it's important for the rest of my argument that the convective zone is touching an optically thin surface of the star. So when I look at these 2 different time scales, the convective transport time and the in-spiral time of the companion, we can see which one is dominant in which region. So anywhere that the convective transport time is less than the in-spiral time, the convection in that region is going to be dominant. And then anywhere that the in-spiral time is less than the convective transport time, in-spiral is dominant. And so we have these 2 different regimes of these time scales, and within these 2 different things, we argue that different things can happen with the efficiency of the interaction based on how the convection is transporting energy from the inspiraling companion. So we say where convection dominates, which is anywhere that the inspiral time is greater than the convective time, the convective eddies of the convective zone can carry the released orbital energy from the decaying orbit's companion, or decaying companion's orbit, to the surface or to an optically thin layer of the star where the energy is lost from the system and radiated away. So this lowers the efficiency of ejection just based on the convective regions and the convective dominance in that zone. So if there's sufficient energy in the interaction, the envelope will get ejected. And you've probably seen plots like this before. We have the binding energy just of the MESA model here in blue, and the change in orbital energy of the companion in the dashed lines. But instead of these starting at the surface of the star, where they start their inspiral, they're starting deeper into the star because the convection is allowing that energy to not contribute to unbinding the envelope. So we say anything where the energy is sufficient ejects the envelope, and then below this line, the companion will shred within the envelope. But the more exciting part is this exciting little graphic that I have made for you. So this is a top-down view of the model that we're using. We have the core of this giant star in blue, the radiative region of the giant star in orange, and the convective region of the giant star in this maroon purple color. And then this is our little companion over here. So top-down view, we'll see that this thing starts to inspiral. We know that, and it'll come closer to the core, ejecting the envelope along the way. So if we zoom in on the boundary between the convective region and the radiative region, that's where things really start to get interesting. So the companion, all the while during its inspiral, is releasing energy. It's transporting energy into the envelope. And those are my little squiggles, is the energy. And the energy cannot contribute to unbinding the envelope because it is being picked up by, it's being picked up by a convective eddy. Here, my nice bubble. And that convective eddy is moving, boiling throughout the envelope of the star, and then carries it away to the surface where the energy can be radiated away, and it's lost from the system. It continues to inspiral. Now it's crossing this boundary into the radiative zone here in orange. And as it does that, it's still contributing energy, but all the energy now, instead of being picked up, is just deposited straight into that zone. All of a sudden, there's a bunch of energy that can get dumped in. And that huge deposition of energy all of a sudden will cause the envelope to be ejected, floats away in my nice cartoon. And what this leaves is your companion in orbit around the central core that's remaining. So when we compare the energy of these things, and I just have two different models here just to show what happens with a lower mass and a higher mass primary. We'll look at this 2 solar mass primary here on the left. Again, the binding energy of the envelope is in blue, and the dashed lines show different companion masses, their change in orbital energy. When we look at this thing, we see that depending on the different time scales of the companion, the convection will make this more or less efficient. So convection will cause the companion to be allowed to travel further into the envelope before contributing the change in orbital energy to unbinding the envelope. So for this example, this convective zone allowed it to travel all the way down to like 2 × 10⁻11 centimeters before all of a sudden a huge deposition of energy comes in and exceeds the binding energy, and this is where the envelope can get ejected. So we say wherever these things intersect is where there's this huge deposition of energy and the envelope is ejected. And this is also where we mark our final separations of the systems, because at this point the envelope is ejected and you have your M dwarf companion or your coupled Jupiter mass companion in orbit around your core, a white dwarf core. So conclusion here is that convection and radiation together allow the companion to travel deep into the envelope before the energy can be tapped to drive ejection. The other thing that we're seeing here is that this is matching the observations of the separations of post-common envelope M-dwarf white dwarfs, where these things are around 10 to the 11 centimeters almost every time. So we also did this analysis with double white dwarfs instead of, so this was M-dwarf white dwarfs. So we do the same analysis, but instead of using a M-dwarf companion, we use a white dwarf companion. And so this changes a couple things about the in spiral, but in essence, it's a lot of the same arguments. So same timescale considerations, same energy arguments, and these are observations from all of these papers and more. And I'm going to overlay on top of this the final separations that the convection considerations allow. So the final separations look something like this. So this is, we see that it covers basically all of these observed systems are covered by at least one of the models that I ran. You'll see a couple interesting features that I can talk about. So the first is this large clump over here, which follows this large clump of observations. These are the extremely low mass white dwarfs, which are called ELMs. And these ELM white dwarfs, these ELM white dwarfs, are clumping around here. And we think that this is because they are, the common envelope is on the RGB instead of the AGB. The other thing that we see here is this overpopulation for the lowest orbital separations. This is most likely due to the fact that I did not use an initial mass function. So we're working on getting this incorporated into some population synthesis codes so we can see if we use an IMF that's physical, is that going to help constrain this plot a little bit better. Okay, so this is matching at least one of these systems every time is matching observations of double white dwarfs. So I'm a fast talker and I went through that really quickly, but I can have plenty of time for questions. So in conclusion, as the companion in spirals through the common envelope, the convection can carry the energy from the decaying orbit of the companion to the surface where it's radiated away. We show that through timescale arguments of the convective time versus the in-spiral time. This allows the companion to travel deeper into the star before the energy can eject the star or the envelope of the star. And this matches observations of M dwarfs and white dwarfs, as well as double white dwarf systems. In the future, we're incorporating this analysis into high mass models. And it's interesting what we're seeing with the high mass models is there's a lot of different things in play, different timescales. But what we see is that the convective timescale and the in-spiral timescale sort of flip. And so the effect that convection is playing that we're seeing in these lower mass models is going to be totally different for the high mass models. So that should hopefully be out in a couple of months. So stay tuned, but I'm looking forward to working on the high mass stuff as well. All right, so that's all for me, and thanks. I'll take questions.
Thank you very much. Questions? So Noam, please go ahead.
Yes, very nice talk, and I agree with you that convection is very important. Also, we worked on this in my group with Dana and Efrat and Ron and Shlomi on the transportation of the recombination energy out, and we claim it's also can radiate away or most of the recombination energy. My question is different here. Convection is important, but when the companion enters to the radiative zone inside, and it releases a huge amount of orbital energy, why doesn't convection start to develop in the radiative zone and carry the energy or part of it out? Because you assume sharp transition between the convective and radiative zone, but as I see it, the spiraling in will deposit energy that will make some of the envelope convection in the zones that were before radiative. This is my question.
Yeah, so that's a good question. My answer, which might be just a quick answer, is that we're looking at the time scales and not necessarily like a break. There's not like a wall between the convective zone and the radiative zone. So with let's see if I can, here, with our time scale argument, we're saying that the convection can no longer dominate. Maybe it would start some convection, but I doubt that convective transport time would all of a sudden drop down all the way so that it would be the more dominant thing to the in spiral. So if convection is starting, I would doubt it would be as rigorous as the convection is in the outermost layers.
Okay. Then Morgan.
Can I follow up on that comment?
Sure.
Almost exactly? And I think, Emily, thanks for this really awesome talk. And I think what I find sort of most kind of conceptually inspiring about this work that you've been doing is that, you know, stars are already set up to transport huge amounts of energy from their interior to their outside. And it's almost like convection itself is almost like a conveyor belt bringing that energy out. And so if we want to do work, like physically move the envelope, then we have to put in more energy than that because the structure is already set up for that.
Right.
But to come back to Noam's comment, I think it will be really interesting to think about how the in spiral of an object changes the structure, and then what that change structure might then be set up to transport. And this is along the lines they've been working a lot, thinking about like later phases, but you know, that I think there's really subtle and interesting questions about like, is the energy deposited as heat in a shell? That would be sort of one approximation. And then you might say, oh, it's instantly convective. Whereas if it's still like kinetic energy, you might get a different answer. So I think this isn't so much a question as like a comment that like, as we go forward, this seems like really of central importance, particularly to phases that are quote unquote slower. Like objects with low mass companions, that sort of thing, that you're showing us here in this plot, for example, and also to sort of structures that have already adapted to some of that energy input by puffing up and becoming less dense and slowing the process down. So I'm really curious about like what you'll find as you start to apply some of this thinking to kind of the puffed up end state of common envelope phases, where you have almost an engine that is the central binary as the heat source. And then you have this extended outer layer. And maybe the final separation depends a lot on that interplay between energy transport and that heat source. Right. So I don't know, I'm really excited to see where this path leads.
Yeah, thanks. And we'll definitely start thinking about that, and we can talk too.
Amazing.
So this final state, Morgan, you were referring to, that's sort of this original idea of this self-regulated spiral in by Meyer.
Yeah.
Right. So that's actually sort of the original idea that they had.
Exactly. And you know, at a certain point, you must like you reach a phase where it's like, I don't need to repeat what you just said, but like if the transport matches the input perfectly, then nothing happens. But clearly there is some degree of out of balance, and maybe that degree of out of balance is really crucial in determining the answer. And I don't know how to ascertain the details of that.
So there's another question by Miguel Santander here in the chat, and that was following Morgan's comment, getting rid of a large fraction of orbital shrinking energy through convective transport implies significantly decreasing the energy budget available for ejecting the whole envelope, doesn't it?
So if I think I understand the question. So we're talking about this plot, I guess. The way that, at least the way that we argue this orbital energy argument is that the little dr that it's moving every time, even just within that little dr, there's enough energy to bump this out. So when you're getting rid of it, I mean, it's radiating away, but there's there, at least in these arguments, there's sufficient energy regardless of the energy that's getting radiated away.
So Ashley, if you want to ask a question, please go ahead.
Thanks, Fritz. Yeah, really nice talk, Emily. Yeah, so this is really exciting work. I'm just wondering, with respect to your models, because you've been modeling, I guess, typical red giants, I presume. I know in binary population synthesis, often a lot of times we see a lot of common envelope events also occur early on the giant branch when the star is more sort of a Hertzsprung gap star. Mm-hmm. I'm just wondering if you've simulated many of those or have plans to look into that in any more detail.
Yeah, so that's what we did for the double white dwarf analysis is we said, you know, no matter where it is in the evolution, when the core matches an observed white dwarf mass, you know, what's the final separation that we're going to get? So some of these lowest mass things are like barely off the main sequence, basically. And we're still finding that we can match with this prescription, kind of this argument, the final separation. So this is kind of an approximation for the age of the star. So we do have some of these young, barely giant stars in the double white dwarf analysis.
Okay, thanks.
Mm-hmm.
So I have another remark on this. So the question here seems to be in these 3D hydro simulations that some of us do, this actually is physics that should be in there, right? I mean, it's convection should be something that should be developing if the stellar structure is correctly set up. Mm-hmm. And so then the question is, what is needed to see these effects and to be sure of our numerical result? Because, I mean, in the end, it's possible to set up the primary star with convection included. So Sebastian Ullmann has done this and shown this in his 2017 paper. It may be a matter of resolution that we need to get here. And so that is perhaps something to think about. And I would like to hear the opinions of other modelers about this. But maybe we can also discuss this later. Maybe, Emily, you have an idea about that? Or...
So the thing that I know is that radiation is something that is often not in these simulations, and radiation is necessary to carry the energy out. And I know that that's a difficult thing for simulations. So that's one of the things that is missing a lot of times.
Okay, Paul, you raised your hand. We can't hear you. I can't hear you.
How about now?
Yes, no.
Okay. Yeah, so I think convection absolutely needs to be in these simulations, but direct simulation is hopeless. And so the question is, what are appropriate closures or models for use in dynamical simulations? You know, we can't rely on simply the dissipation of the simulations at the scales that we can resolve. So, sort of implicit LES is effectively what we're doing, and I don't think that's sufficient.
So, Paul, is your hopelessness in terms of resolution?
Yeah. The Reynolds number of like the surface layers of the sun is enormous, and right. It's just outside of any plausible range of computing ability.
Okay, other comments or questions? Not, let's thank Emily again. Thank you very much for this very nice presentation. Now we have the last talk of today's, or of the first session of today. That's by Iminhaj Ahmed about the possible core mergers inside common envelopes. So please, if possible, go ahead and share your screen.
Hello, can you hear me?
Yes. Okay, it works. So please go ahead.
First, hello everyone. My name is Iminaji. I work at NOAC Beijing. Here it's almost midnight. So thanks for giving me this opportunity to give a talk in this amazing event. So in this talk, I will introduce, I will mainly show how this common envelope is important to produce some special objects and transients by introducing my two recent works. So in this slide, I drew a figure to show importance of binary in astrophysics, and common envelope, of course, is a very important, crucial case in binary, which is related with so many special objects and transients. So previous talks, some speakers already talked about the importance of binary population synthesis method. In this method, we use some initial inputs and then run a large of binary systems to see how some physical parameters affect the outcomes. For the common envelope, the common envelope efficiency parameter and the binding energy parameter, these two parameters are very important. BPS can give some information to constrain these two parameters. So in the first work, I propose a co-merger induced detonation model. So in this model, I consider mergers between the carbon-oxygen white dwarf with the core of the companions. For the companions, I consider three cases: intermediate core of the intermediate hydrogen-rich normal star, and the core of a stripped helium star, and then core of massive stars. So especially in this work, the merger between the carbon-oxygen with the core of massive stars is very important because it's motivated by the science work, observational work by Jacob 2020. So in this work, they observe, the observation shows that the supernova, superluminous supernova 2006 GY may be exploded from carbon-oxygen white dwarf. So based on this work, and then based on the ANORM's work, ANORM showed the co-degenerate model, which is also based on the co-mergers inside CE. So in this model, as I said, I considered carbon-oxygen white dwarf merges with core of its companion. And then in this BPS model, I mainly considered 5 models, considering the different alpha, different lambda, and critical mass ratio, and also considered different initial metallicity. So with the merger of carbon-oxygen white dwarf with the core of intermediate mass, I propose this may sources for type 1a supernovae, because the combined mass of the carbon oxygen white dwarf and core can exceed Chandrasekhar limit mass. So in this case, that's for the next works. In this works, I considered the double detonation model. Based on that, I considered 0.9 core carbon oxygen white dwarf, and then 1 solar mass carbon oxygen white dwarf with a core mass larger than 0.6 solar mass, and then merge. And when they merge, the helium core of the companion can surround the white dwarf, and then the helium-rich material can be ignited, and then this detonation can trigger the carbon detonation of the white dwarf. So this is basically the same as the double detonation model. Only difference is this evolutionary pathway is different. This table shows my BPS results rates with for the different cases for different models. So this is the initial mass distribution and the final mass distribution when the merger going to happen inside the C. So you can see the involved mass here. The combined core mass is almost all larger than the Chandrasekhar limit mass. So it's definitely maybe a source for type 1a supernovae. And some fractions of the combined mass are larger than the 2 solar mass. So this type of binary mergers can be sources for overluminous type 1a supernovae. So this is one typical example for the mergers, which is example for the supernova 2006 GY. So you can see that here, inside the common envelope, the white dwarf mass is larger than 1, and then the helium the co-helium mass is kind of more than 3 solar mass. Most importantly, it has larger than 10 solar mass common envelope, hydrogen-rich envelope. So this condition is match the conditions raised by this science paper, observational paper. So this may be exploded as superluminous supernovae. So this is for the merger between the carbon-oxygen white dwarf mass and the helium core mass of the massive stars. This is the merger rates for different cases. And then I found that the merger rates can explain this observational rate of the superluminous supernovae. So this is same with last figure I showed, but this is for the massive stars. So you can see this involved mass, this right lower figure. So you can see that involved mass larger than 7 solar mass. So the mergers between the carbon-oxygen white dwarf mass and the massive stars, cores of massive stars, can have a very large involved mass. And then, so combined core mass also larger than 2 solar mass. So they may be sources for very peculiar transients like supernovae and supernovae. This is a main conclusion for this work. So yeah. In this way, the core mergers between carbon oxygen white dwarf with the cores of its companions can be origins for the type 1A supernovae with the interaction with circumstantial material, and then also can be origin for the type 1AX supernovae, and then the core mergers with the core of the massive stars can be origins for the supernovae. So in the second work, I just consider what if is a carbon oxygen white dwarf instead of carbon oxygen white dwarf, it's what if it's oxygen neon white dwarf. So I found that I propose a co-merger induced collapse model. So through this model, the co-object can be formed, and then magnetars formed, and then this neutron star systems objects can finally evolve to black holes. And then because of this new boron objects with this model can have a very large, massive, CEV, so massive involve. So they can interact with this involve. They may trigger some peculiar supernovae, like supernovae. So I just talked about moderation. So this is one typical example for this this model. So you can see here the last stage is a common involve. So you can see the white dwarf mass is very big enough, and then the company is kind of 13 solar mass. So they this merger. So yeah, this merger can cause like accretion-induced collapse can form a neutron star object with a very massive involve. So another question is, what if this white dwarf is magnetized? Another interesting thing is previous talks already mentioned that this magnetic field can be amplified inside the sea. So in this with this substance, the magnetar also may be formed in this way. So if the magnetars, and then if it's not magnetized, it may be a pulsar, or like if the involved mass is very large, it may be a TZO. So there's central objects can interact with the massive involved, and then finally can trigger some peculiar transients like supernovae. So this is another example. Difference is this one is total mass is lower than 15 solar mass. This in this example is total mass larger than 15 solar mass. So with current stellar some stellar models, we propose if the total the combined core mass and the involved mass larger than 15 solar mass, it may eventually evolve to a black hole because central objects, even if it's neutron star, it can accrete matters very quickly. There is a very quick transition from the neutron star to a black hole in this evolution pathway.
2 minutes.
So, you can see the combined, the involved mass also is a lower panel, a right lunar figure. So envelope mass also can be up to 17 solar mass. So it's enough for forms these special objects. So this is a combined mass distribution. So there is some fraction actually larger than 15 solar mass, which may finally form a black hole. So this is a conclusion for this work. So actually, some other models shows the central objects, how the central objects can trigger some transients like supernovae and fast radio bursts. So I don't talk about the details, but in this way we may produce some peculiar transients. So summary of my talk is co-mergers inside the common envelope are very important. I already show you that some special objects like TZO, magnetars, pulsars, and black holes may be formed from the co-mergers inside the common envelope of white dwarf binaries. So this evolutionary pathway is very, very important. And then this new born objects through this way with these two models can trigger some special peculiar transients like CSMs, type 1 supernovae, 1AX supernovae, and then superchandra Saha overluminous supernovae, and then may also trigger some superluminous supernovae. So the co-mergers models may be very important than we thought before. And for the future, higher dimensional simulations and observational works hopefully will provide some constraints for what we propose in these works. Thank you.
Thank you very much. Questions? Minhaji. Okay, yeah, go on.
Yeah, I just want to say, Minhaji, thank you very much for bringing this important issue. Not all common envelope are ejected. Some will not be ejected, meaning that the companion will merge with the core or will be destroyed by the core or will destroy the core. If it's a neutron star, it can destroy the core. If it's a main sequence star, it can be destroyed by the core. If it's a white dwarf, it will merge, as you discussed. Take supernova 87A. We think that it was shaped by, you see the ring, nice 3 rings, were shaped by a companion that entered the common envelope. We don't see the companion there anymore, so it probably merged or were destroyed by the core. And indeed, white dwarfs, I expect to have the largest rate of merger relative to their mass, because I don't expect them to launch jets. And even if they accrete matter, they start to burn it and form another giant inside the common envelope, if you like. So yes, it's a very important work that you do to try to show what carbon, oxygen, and helium, and oxygen, neon, magnesium, white dwarf can do in the merger. But this is something that the simulation did not get into yet, to do the simulation inside the common envelope of the merger itself. So keep on with the good work. This is my comment.
Thank you.
Okay, other questions? So I have one. You said that a way to form a magnetar in the end is that you actually amplify the magnetic field in the common envelope phase itself, right? What field strength do you need to reach there? So what field strength?
I can hear you.
Yeah, what field strength do you need to reach there in order to form a magnetar? And what do you think? How much you need to amplify the magnetic fields in the common envelope?
For that, this BPS, we cannot calculate that. So I just assume that if a white dwarf magnetized larger than like 10 to 7 Gauss, then they may finally become a magnetizer.
Yeah. Well, from our common envelope simulations, actually we reached some 100 kilogauss or so, but not more. But if you actually sort of in the end merge the central objects, right? So that actually may amplify your magnetic field more than the common envelope itself.
Yes. So for this BPS, we cannot, we cannot calculate how actually they amplified. We just use the assumption.
Okay. All right. Other questions or comments? If not, then I would like to thank all the speakers in this session. And I think we now have a 55 minutes break and start then again with the second part of simulations and models that's chaired by Paul Rickert.
Don't you want to have a general discussion now or for 15 minutes, 20? This is our aim is to have discussion at the end of each session.
Yeah, we could either do it now or after this the next session. So whatever.
Yes, I don't know. It's up to you and Paul. How do you want to split it?
Either way is fine with me.
Yeah, I think maybe we combine these things because yesterday we also had the discussion after the two parts of the session, right?
Well, we had one session besides the opening discussion, but if you like to have it, so yes, Paul, keep the time in the next session so we have at least half an hour for final discussion of the day.
Gotcha.
Unless, I don't know, if it's up to you, Fritz and Paul, how do you like to split it? Just decide now, I don't know.
Okay, well, we can leave time for discussion at the end.
Okay, so we'll start exactly in 55 minutes and have a long discussion at the end of the day.
Yep.
Okay.